So for this first problem, we're trying to figure out how much lead is in this water. And the equation to calculate parts per million is grams of solute divided by grams of solution. And in this case, the solution is this 500 liters of water. Since it's water, the density is going to be pretty darn close to 1 regardless, so we'll just use that. But I need grams of solution. So 500 liters is equal to 500,000 milliliters. And if the density is 1, then what's the mass? 500,000 grams. And so I'm trying to find out my grams of lead in this problem. And the denominator here is 500,000 grams times a million equals 7 parts per million. So this calculation is just 7 times 500,000 divided by a million. And that'll give us grams of lead. And 3.5. All right, that makes sense. Yeah.
Then I put 4.
Sure, that sounds good. 4 grams of lead in this water. Okay. List these in order of best to worst electrolyte. So which one's the best electrolyte? Yeah, this one's the best because it gives us 3 particles. Which one's the next best? Nope. I'm sorry, you said the NABR?
Yeah.
Sorta.
Why put the NABR in?
This one and this one both have a +1, -1 charge. So these are both tied for number 2. And then this is not going to dissolve at all, right? So this will be 1. So the best one is going to be this one. And the worst one is going to be this one. And then these 2 guys are tied for being in the middle. How about this why chemical reactions occur question? What do substances want to do?
Lose energy and become disordered.
Lose energy, which is enthalpy, right? And
Become disordered.
sure. So less of that and more of that. The diamonds are for everything. What's wrong with that?
Though they're forever maybe in our lifetime, eventually it's just attacking the carbon.
Well, it is carbon.
Well,
It
I guess
starts out very orderly, so it's gonna
It's
break
a
down.
substructure.
It's got graphite.
So the crystal metric structure is organized, and because it's organized, nature doesn't like that. So it will break apart, and that's just entropy doing its thing. So entropy is, what does it measure? So its symbol is an S, and its units are usually kilojoules per mole times Kelvin. And remember, it's a measure of disorder, not order. So if you have more entropy, the thing is more disorganized. And the enthalpy,
energy, existence of energy.
and its symbol is an H, and it's just kilojoules per mole. You can kind of think about it being like energy density. how much energy I have per unit stuff. And gives free energy. What's the definition for it?
Tells you whether a reaction will be spontaneous or non-spontaneous.
Okay. I have no idea how to spell spontaneity. I-N or E? T-A-I? That looks terrible, but
It's wrong, but that's right.
spontaneity. Yeah, okay. And its symbol is a G, and its units are kilojoules per mole. Given a reaction, a given reaction is endothermic and becomes more ordered. Is this a spontaneous reaction? Explain your answer. Okay, so if it's endothermic, what does that mean?
Absorbing energy.
Yeah, so that prefix endo means in, thermic meaning energy. So these reactants have less energy than the products. So that means the H goes up. So nature's not happy with that. And it becomes more ordered. So my S goes down. So does that happen on its own? No, non. Definitely non-spontaneous. The easiest example of that is charging your cell phone battery. The lithium-ion battery becomes more organized in its solid crystal matrix structure, and it has more energy. Did you get tricked with this one? Think so? What's the tricky thing on this one?
You have to change it to custom.
Anything else? That's the slightly tricky thing. The slightly more tricky thing is one's in joules and one's in kilojoules. Right? And since they're terms, addition and subtraction, that the units have to be the same for you to do anything with them. So if my equation is delta G is equal to delta H minus T delta S, and my delta H is this 4.1 kilojoules. So here I've got kilojoules and here I've got joules. Just swap one of them. It's probably easier to turn the kilojoules into joules. So what number do I use? 4.1 turns into 4,100. Move the decimal place over 3 spots. Okay. So I'm going to write 4100 joules per mole here. And then I'm going to subtract off 273 plus 19, 280, 92. 292K. So 292K, and then I'll multiply that by 12 joules per mole Kelvin. The K cancels out. And so now they both have units of joules per mole. So we've got 4,100 minus 292 times 12. And I get 596 joules per mole. So what's the answer to this question? No. The G value is, delta G value is positive, right? 596. If the G value is positive, that means it's a non-spontaneous reaction. That means you need to put energy into this to get it to go. Okay. What about at 78 degrees Celsius? So now I got to take this 273 and add 78 to it. So 351, okay. So then I'll put 4,100 joules per mole minus 351 K times 12 joules per mole Kelvin. The Kelvins cancel out. And this time I get 351. This time I get a negative 112 joules per mole. So what's the answer this time? Yes. So whatever this chemical reaction is, what happens to the organization? More disorganized, right? It's a positive S, delta S. That means the entropy went up. So that means these things became more disordered, and nature's happy with that. But what happened to the H? The enthalpy. It also went up, which means that the reactants have less energy than the products, and nature doesn't want that to happen. So these two things were fighting each other. And in that circumstance, at a higher temperature, the substance will be spontaneous, and at a lower temperature, the reaction will be non-spontaneous. Okay. This next one here, explain how you would make 500 milliliters. Okay, so in the lab that you guys did last week, you made a concentrated solution of, what was it, copper sulfate? And then you took that concentrated solution and you made a much larger dilute solution. Did you care how much concentrated solution was in the container? You just need to have enough, right? So in this particular problem, we're being told that I've got 2.5 liters of the concentrated. I don't really care unless I need to use more than 200 or 2.5 liters, which I don't, since I only want to make 500 milliliters. So I don't really care what the volume of the concentrated solution is. That's what I'm looking for. What I need out of this is an explanation of how to make it. So I need to know how much of the concentrated stuff to put in my 500 milliliter volumetric flask. Are we okay with that? So my answer for this particular calculation needs to be milliliters. So I'm going to put 500 milliliters right here. So now I need to use my two concentration units to determine how much of the concentrated stuff I need. So it'll be moles per liter divided by moles per liter, and then those guys will cancel out, and I'll get milliliters. So is the number that I need going to be bigger or smaller than 500? It's got to be smaller. My end volume is 500. We're asking how much of the concentrated stuff do I need to put in this 500 milliliter container so I can fill the rest of it up with water. So I need a number significantly smaller than 500 milliliters. Okay, so I've got two concentration numbers. I'm just going to put the small one in the numerator and the large one in the denominator. That will make me get a number in milliliters that's smaller than 500. So it's 500 times 0.25 divided by 12.1, and I get 10.3. So that actually didn't answer the question, though. The question would be, to answer this question, you need to say something like, add 10.3 milliliters of 12.1 molar HCl to a 500 milliliter vol flask. Fill near line with water, and then fill to line with dropper, and then invert. That'll just mix it up. Since they're both liquids, I don't need to do that. Fill it halfway and then shake until it dissolves. Everything's already dissolved. So I just need them to be in the same container and then flip it over one time and then they'll mix themselves. Technically, if you didn't need it for like 20 minutes, you wouldn't have to do anything at all. You just put them together and they'll mix themselves. Okay, for this last one here, we're gonna explain how to make 500 milliliters of 1.25 molar sodium hydrogen carbonate given sodium hydrogen carbonate solid. So it's NaHCO3. So we got for molar mass for that. So 1.00795 plus 12.011 plus 15.9994 times 3 plus 22.9898. Is that right? 9898? Sure. And so I get a molar mass of 83.9903 grams per mole. Okay. So what I'm going to do with this is determine how much of the stuff I'm going to need solid-wise. And so I'm going to do that by putting 1.25 moles NaHCO3 divided by liters. And then I'm going to put 0.5 liters here to cancel the liter out. And then I'll put 1 mole NaHCO3. And I'll put 83.9903 grams sodium bicarbonate. All right, so times 0.5 times 1.25. So I get 52.4939 grams. All right, so add this 52.4939 grams of NaHCO3 to a 500 milliliter vol flask. Let's say 2/3 fill with water. Mix. Dissolve. 4, fill near line. And then fill 2 line with dropper. And invert it. And you're good to go. Do you have any questions?